Okay, up until now, the examples that we've been using for the colligative properties have all been non-electrolytes. But since colligative properties depend on the concentration of the particles, then we do need to make a slight adjustment when we're dealing with electrolytes, because with electrolytes, they dissociate in water and we get multiple particles per one formula unit of the electrolyte. So if we look here, an example, if we have a 1 mol solution of urea, that's a non-electrolyte, has 1 mole of solute particles per liter, while if I have a 1 mol solution of sodium chloride, I'm going to get, right, I'll get sodium ions and I'll get chloride ions. So I get 2 moles of solute particles per liter. Oops. Wrote over my thing. Okay, so we have a term called the Vant-Hoff factor, and we use that to modify our colligative property equations when we're dealing with electrolytes. And so it's very important to remember that if you're dealing with electrolyte, you're going to have to put this factor in there. Essentially, you're taking the molality of the substance and multiplying by the number of particles you get per one unit of the substance. And so we can take our equations we've been dealing with so far and just put this Vant-Hoff factor in there. Okay, for non-electrolytes, I would be 1. For electrolytes, it's about equal to the number of ions that it dissociates into. Okay, it does vary somewhat with concentration. The more concentrated the solution is, the greater the variation is away from the number of particles it dissociates into. Okay, so here we can look and see. Here I have sodium chloride, and as you can see, the more dilute it gets, the more it approaches the 2 that it would have if it completely dissociates. And that's basically because the more concentrated it is, then you can get kind of some repairing of the cation and anion, and so that they kind of act like one particle rather than 2 separate ones. And so the more concentrated, the more crowded the particles are, and the more likely this is to occur. And so these tables that you see here actually measure they look at like the freezing point depression or the different colligative properties, and they can measure for a given concentration what is the Vant-Hoff factor for a particular solute. Okay, so let's look at some problems here. Here I have vapor pressure of water at 20 degrees Celsius is 2.33 kilopascals. And if the solute is made from 10 grams of sodium chloride in 1 kilogram of water, and we assume it dissociates completely, we want to know what's the vapor pressure of the solution at 20 degrees Celsius. Well, okay, vapor pressure, when we have a solute, we're talking about Raoult's law. All right, and we kind of talked about Raoult's law in a previous discussion, but really Raoult's law describes the effect of a solute on vapor pressure, which is a colligative property. So it's perfectly fine to look at it here because it would apply. So what did Raoult's law say? It said that the vapor pressure of the solution is mole fraction of the solvent times the vapor pressure of the pure solvent. Okay, now here the thing we have to realize is that when we're finding the mole fraction, we have to take into account, we want the moles of solute is going to be the moles of solute particles. So if I have 10 grams of sodium chloride, for example, and that is going to be about 58 grams in 1 mole of sodium chloride. Okay, and so it's going to completely dissociate. So for every 1 mole of sodium chloride, I get 2 moles of solute particles. All right, a Vant-Hoff factor of 2. So 10 divided by the 58 times 2, so I get 0.345 moles of my solute. And I have 1 kilogram of water, so 1,000 grams of H2O, 18 grams in a mole. So I have 55.6 moles of the water. So the vapor pressure of my solution is going to equal 55.6 moles divided by 55.6 plus 0.345 moles times the 2.33 kilopascal. And that's going to give me 0.994 times 2.33. So 2.32. So not much of a change because relative to the amount of solvent, we had very little solute in there. But still, we looked at 2 moles of solute particles because we had an electrolyte there. We had to multiply our molarity, or our moles, times 2. All right, which aqueous solution, if either, would have the higher boiling point? If I have 0.5 molal sodium iodide or 0.5 molal sodium carbonate, okay, delta T boiling is going to equal IM KB. Well, for both solutions, this is the same and that's the same. The molality and the constant would be the same. However, I would not. For this one, if we assume complete dissociation, I would be 2, whereas for the sodium carbonate, I is 3, because I get 2 sodium ions, 1 carbonate ion. So the sodium carbonate would have a higher boiling point, would produce a higher boiling point. Okay. Here we have calculate the molarity of a solution containing potassium chloride and water if the osmotic pressure at 21 degrees Celsius is 100 torr. Okay, 760 torr. It's 1 atmosphere, so that's going to be 0.132 atmospheres, and this is 294 Kelvin. And so I is 2 if it's KCl, and so with the I there, so we have 0.132 atmospheres. It's 2 times the molarity, which is what we're trying to find, 0.8206 and 294 Kelvin. So I'm getting a molarity of 0.0027. That's moles per liter. Okay.